In this chapter, we're going to do Vacisek2, which is going to cover a new term structure for the short rate, and then we're going to learn how to price different bonds and how to compute their deltas and their gammas under the new Vacisek tree. These are the suggested reading. So the highlights of the chapter is the first thing we're going to do is a more realistic tree for the short rate. Then we're going to see how to price bonds of any maturity under this new tree. And remember that this tree is based on the Vacisek model. And finally, we're going to see how to manage the risk of a bond portfolio in this Vacisek model. Now, here we're going to have this type of notation, which is going to be TRS. For example, we're going to see 0R1, which is the rate observed at time 0, and that goes from time 0 to time 1. Okay, so this is the same thing that 0R0, 1. And then we're also going to see new rates that are going to be called like 1R1, 2, which is the rate that it's going to go from time 1 to 2 and is observed at time 1. This, we're also going to write it as R1, 2. And here you understand that this rate goes from time 1 to time 2. So it's a 1 year rate. Now, the fact that we put this 1 in here means that this rate is observed in year 1. So this is a characteristic of the trees that you are trying to see what the different possibilities are in the future. So that's why this rate here at 1 is a rate that is going to be observed in period 1. So first, let's see what the theories of the term structure are. So here I'm going to put some of them. These are not all of them. So the first one is something called the unbiased expectation hypothesis. Now, in the unbiased expectation hypothesis, you have that the expected value of a future rate is equal to the forward rate. When we saw the chapter on forward rates, we saw that the expected value of a rate is not its forward rate. However, this is the assumption that is made in this unbiased expectation hypothesis. Now, a second term structure theory is the one where you have preferences for liquidity. So riskier long-term bonds must offer a risk premium over the short rate. Why? Well, because if I ask you when do you want to receive your money, like in 1 year or in 30 years, well, you're going to say, no, in 1 year, like I don't want to wait that long. So you have a liquidity preference. So it's not the same thing to invest every year in 1 year bonds for 30 years than to invest just in one 30-year bond now. So why? Well, because of the liquidity. So if you decide to invest in this bond, you're going to have to get a premium on top of the strategy. Hence, the rates for the 30-year must be much higher than just reinvesting in the 1 year bond. And then finally, and this is the one that actually we're going to do in this chapter and that we have done in the previous chapter, is called the local expectation hypothesis. So the local expectation hypothesis is the one where the expected bond return of the first bond is equal to the second bond, and it's always equal to the risk-free rate. That means if today, let's say you buy a 10-year bond, a 30-year bond, and a 100-year bond, they all are going to have exactly the same rate of return, which is going to be R, which is the risk-free rate. Is this realistic? Again, it's not. Why? Why not? Because you always expect to get, for certain bonds, a higher rate of return, depending on the maturity and so on. But here, this is the assumption. Now, let's go back to the tree that we saw in the previous chapter. So in this case, we're going to assume that we're going to have a maturity of 2 years. H, the space between the nodes, is going to be 1 year. Mu, the long run mean, is going to be 6%. Sigma, 4%. The mean reversion parameter phi is going to be 0.8. And our starting short rate is 7%. So first, we're going to compute the step. So the step is going to be equal to 2.67%. And then this is going to be the formula for the probability. So remember that the probabilities are going to change depending on what node you're in. So here I fill it up for you. So you should do this yourself to make sure that you know how to compute these rates with the slides on the previous chapter. So our initial rate is the 7%, and then it's going to go up to 7 plus 2.67. And then here 7 plus 2 times 2.67, and so on. And then here I computed the probabilities for the different nodes. So you have to compute this 3, and then the one below here is the 1 minus 0.35, for example. Or this one here again, 1 minus 0.57. So when we have this tree, the next question we want to answer is, what is the term structure on each one of the nodes? Why? Well, because this rates that we computed, so this 0 rate was the rate that goes from year 0 to year 1. And then the short rate in year 1 is the rate that goes from year 1 to year 2. That's why they're called short rates. They go from the time span that there is between two nodes, that means H. And there's one from time 2 to time 3. But now we're missing the term structure. So for example, at time 0, we're missing the 2-year rate and the 3-year rate. And then at time 1, we're missing, this would be like a 2-year rate, the one that goes from year 1 up to year 3. And here we're missing, again, the 2-year rate. So now the question is, how do we get these rates of the term structure? So now we want to know what is the value of a 2-year bond at t equals 0. So first we have to look at the graph of the different payoffs of this bond. So imagine that you have time 0, you have the 1-year rate. So this one would be the 0R1, which is 7%. And now from time 1 to time 2, you're going to have not 1, but 2 rates. So here you're going to have that with probability 46%, the 1R2 is going to be 9.67%, and with 54% probability, the rate is going to be equal to 4.33. So then the question is, how can you discount $1 at time 2 to get the price at time 0? And then when we get the price of this, this is going to be the 0D2. It's going to allow us to get our 0R2. So what do we do exactly? The price of our bond, or of that 2-year bond, it's going to be equal to E to the minus H t minus h rt. So this is the discounting part. And then here we have to multiply this by the expected time t payoff. So let's translate this into our discount factor. So this would mean that 0d2 would be equal to, let's do the first part, the 0r1. So it's going to be e to the minus 7%. And then we have to do here the expectation of the second part, which is going to be 0.46 times e to the minus 9.67 plus the 54% times e to the minus 4.33%, here percent as well. And then this is going to be equal to 0.8716. And this would mean that the 0R2 is going to be equal to 6.87%. Now let's compute the same value of a 2-year bond, but now we're going to do it for the up scenario in year 1. So in this case, the graph is going to look as follows. Since we're standing in year 1, then we're only interested in whatever happens between year 1 and 3. So here the discount rate would be 9.67. And from year 2 to 3, we're going to have 2 rates. So the first one is with probability of 35%, we can have a rate of 12.34. And with probability of 65%, we're going to have a rate of 7%. So then we go and compute 1d3. This would be the value of a 2-year bond in year 1. So this is going to be equal to, we take our dollar, we discount it at the 9.67 rate, and then we multiply this by the expected value of what's going to happen between year 2 and 3. And this is going to be equal to 0.8312, which means that 1R3 in the up scenario is going to be equal to 9.25%. Finally, we do the same thing for the down scenario in year 1. In this case, we're going to get 1d3 down. It's going to be equal to e to the minus 4.3% multiplied by 57% e to the minus 7% plus the probability down, which is 43% e to the minus 1.66%, and then we get 0.914. Hence, the 1R3 down is going to be equal to 4.50%. If we go back to our tree, what we have computed so far are the 2-year rates, which is this is a 2-year rate, this is a 2-year rate, and this is a 2-year rate. Now we're left with 0R3. So 0R3 is going to be what we call a maturity greater than 2 years. And to compute the 0R3, we have to do something different. We have to resort to something called replicating portfolios. So we're going to need replicating portfolios to get the value of the 3-year bond at t equals 0. So what do we have now to do that? We have a 1-year bond that we already know the price at time 0 and at time 1. We have a 2-year bond for which we also know the prices at time 0 and at time 1, and a 3-year bond for which we know the price at time 1, but we don't know the price at time 0. So in this one, in the 1-year bond, let's see what I mean by knowing the price. In the up scenario, we know that a 1-year bond in 1 year, it's gonna be worth exactly $1 in the up and the down scenario. And then today, it's worth the discount factor 1, the 0D1, which is going to be equal, if you compute it from the rates, to 0.9324. This is e to the minus 7%. Now, for the 2-year bond, we also have the same prices. So here we have 0.9078 that you can get it from the rate, 0.9576, and 0.8716 that we got from the previous procedure. Finally, here we have the 0.8312 in the up scenario, the 0.9140 in the down scenario, and this is what we're looking for. This would be the 0D3. What is going to be our replicating portfolio strategy? So replicating portfolio strategy is going to be, how can I get the 3-year bond with the 1 year plus, and this plus is, quotation, with the 2-year bond. So let's set up our 2 equations, 2 unknowns, which are going to be similar in spirit to what we did before, but they're not going to be the same. So let's see exactly what I mean by that. So now what we're going to match is the up scenario, the down scenario, and then when we do the up scenario and the down scenario, we're going to be able to get the 0D3 at time 0. So the up scenario, we would be the 3-year bond pays 0.8312, and then it asks how many units of bond 1 do I need. So this would be 1, since it pays $1, 1 and 1 plus 0.9078 and 2. In the down scenario, 3-year bond pays 0.9140 equals 1 and 1. That's how much the 1-year bond pays, plus 0.9576 and 2. Now, when we solve for N1 and N2, we obtain that N1 is equal to minus 0.678 and N2 is equal to 1.66. Then from this, we can derive 0D3. So 0D3 is going to be equal to 0D1 and 1 plus 0D2 and 2. In this case, we replace. So 0D1 is 0.934 and N1 is minus 0.678. 0D2 is 0.8716 times N2, 1.66. And this is equal to 0.8168. From this, we can deduce what the 0R3 rate is in continuous compounding, and we get 6.74%. So let's summarize what we did. The steps to construct the Vacisek term structure under the local expectation hypothesis. So first, we drew the tree for the short rate. So these were like the 0R1, the 1R2, and so on. Then we computed the price for maturities longer than 2H by taking this discounted expected price. That's when we use our probabilities. And since we deduced here the 0D2, for example, then we deduced the interest rates from the 0D2 prices. Finally, we repeated steps 2 and 3, but now instead of using the discounted expected option price, what we did is we set up a replicating portfolio where we used the 1 year and the 2-year bond to replicate, in this case, the 3-year bond. Now, if you had 4-year, 5-year, it would be the same methodology. Even though this is a very convenient tree, it has some problems, this local expectation hypothesis. So the first problem is that it's not realistic. The type of term structure that we're going to get is going to be very flat. What do I mean by flat? That when you plot time against the 0 rates, you're going to see something very, very flat. And the reason it's going to be very flat is because it does not include any premium. So there's not something like the term premium or the liquidity premium or any premium whatsoever. And now the second problem is that bondholders are not going to receive any reward above the risk-free rate. As we saw, the expected return of a bond is equal to the risk-free rate. And this isn't realistic either.